Hello and welcome to another episode of How to Understand X. Today we're going to be talking about sequences. And I know what you're thinking. Well, if you know what a sequence is, you might be saying that this does not need to be said in more than like 2 seconds. And while I do generally agree, I think that, at least for calculus students, understanding like the super intricate ideas of sequences isn't really important. But I think that if you understand sequences to a good degree, I think series are a lot easier to get, especially in determining the convergence or divergence of certain series. And it's also just like cool, I think. Like I think there's some pretty interesting ideas within sequences that, you can find like general trends and like partial sums and stuff. And I think it's rather interesting. But, you know, I do agree that sequences aren't inherently a complicated idea, but let's talk about what a sequence even is. A sequence it's pretty similar to a set. It's just an assembly of objects or elements in which order matters. Um, and at least for us, we're going to be using the more like mathematical definition because, sequences can include strings for computer science, like, and again, order matters in all sequences regardless of the context in which they're used. Like, for example, in terms of computer science, strings are just like assemblies of characters and letters and like numbers and stuff, um, that are usually bounded by quotation marks or single quotes. But God, which is a valid string, is different in meaning and value from Dog. Like, since D comes before G in the alphabet, the like first letter has like a, I think, lower value than the like G. It depends on what language you're using, but regardless, God and Dog, even in real life in terms of words, they obviously have different meanings, right? And it's a similar idea with sequences. Like, even though you might have the same terms, the like values and what's happening is actually different. But for our purposes, a sequence is just a assembly of elements, and the domain is an interval of integers. So domain will be either z or n, right? This is natural numbers and this is integers. I think for series, we're going to be focusing almost solely on natural numbers, but, you know, it really depends. Like, I think once you get to higher level calculus, you might want to, expand that definition, but, for doing the convergence or divergence of certain sequences, I think it doesn't really matter if you're using um, in integers or natural numbers. And that might seem a little bit strange because it's a little bit like a function, right? Sequences are pretty similar to functions in that you have an input that is modified and made to be output. They're usually, I wouldn't even say usually, I would say sometimes they are, one to one. They fit the definition of a function in that they are one to one. And they're, for every value, for every x there's a y, and for every y there's an x. So it's almost like a bijection. But the one thing that I think distinguishes functions from sequences, at least in the way that we think about it, is the interval or the domain, right? Because functions, like say f of x, is equal to um, x squared. We'll say that's our parent function for every important thing. F of x is equal to x squared. This is continuous on R, the um, R, which is the set of real values, or this is where, yeah, sorry, I confused myself. Q is rational values, R is real values, but this is continuous on all possible values of R in this negative infinity to infinity, and it looks like this. And that's great. It is continuous for every possible decimal, every possible like real value, like pi can be a valid x, and you will get a valid f of x. But n, which is what we're probably going to be using for most of our series and sequences in the future, though x will make an appearance, we have n squared. And instead of using f of x, just to denote that this is a sequence and not a function, or not like a function that we think of it, we say that this is a sub n. Sub meaning subscript, and of course if it was a sup n or a superscript n, we'd write it like that. But we have a sub n is equal to n squared. And again, if you plugged in values of x, you'd get x squared, and if you plugged in values of n, you'd get n squared. But this sequence, well, we usually have to define what like set of values we're going to be using. Like you might see it as a sub n with n in natural numbers, which means that you start at 1 and you go to infinity, right? That was the worst infinity I think I've ever drawn. But still, the idea is the same. You have this sequence, a sub n, and this defines like the interval of values in which you can use it, so n in natural numbers. But we're going to say that for our purposes, this sequence, a sub n is equal to n squared, is going to be, we can even say z. We can even say z just to show how different these look. Not very good at drawing right now. We're going to do like this, like this, like this, and like this. And so we're going to say this is 3, 2, 1, 1, 2, 3, and then that's 0. And as you might notice, it's hard to draw dots with my fingers, but there is only dots, right? The only outputs are created by valid inputs, and if valid inputs are only on this interval of z, which is integers, you're only going to have outputs at every single like integer value. So negative 3 will have an output, but negative 2.5 won't have an output. And negative 2 will have an output, but negative 1.5 won't have an output. And real numbers like pi and e, they won't have values on this like sequence because they are not valid inputs. So you can't get a valid output, right? So just like visually, I know it's not visually much to look at, but visually I think it makes sense to at least think of sequences as their own kind of thing, separate from functions, because the actual ideas that are inherent to functions are slightly different from sequences. But that doesn't mean you can't like apply some of the same things that you know about functions to sequences. For example, and this was a very good transition into infinite sequences. Like we touched on that a little bit beforehand. So a sub n, I'm gonna go back to natural numbers, even though that might seem a little bit confusing. We're gonna go n in like n, so n in natural numbers is equal to n squared. This is an infinite sequence, right? Because you are starting at n is equal to 1, and you are going through every single value of n on n. And I actually forgot to say, for functions and sequences, I think the best way to think about it is that on negative infinity to infinity, on r, there is an uncountably infinite number of possible inputs, right? Because r is uncountably infinite, even between two integers. Like, in between 0 and 1, there's an uncountably infinite number of real values, but there is a countably infinite number of integer values, or natural number values. And that's like a good way to differentiate like regular functions from sequences in your head. Just for regular functions, there is an uncountably infinite number of valid inputs, and for sequences, there is a countably infinite number of valid inputs. So yeah, for n in n, you're starting at n is equal to 1, n is equal to 2, and you're going on and on, right? And yeah, so this is an infinite sequence, right? For every single input, every valid input, there's an output, and there's a countably infinite number of inputs and outputs. So the most important thing in like sequence limits is understanding that they work relatively similar um, to normal functions. So, for example, if we say a sub n, not like that. If we say that a sub n with n in natural numbers is equal to 1 over n, right? And I'm just going to do like n behavior. We talked about that in the limit video, but essentially it's what values, if any, a function is approaching as the input approaches positive or negative infinity. We're going to say that this is going to look like that. I know this isn't the best illustration, but it does get the job done, right? There are only inputs for, there are only outputs for valid inputs, so we're only going to have values. That's actually not going to be a value because you can't divide by 0, but you're only going to have an output for a valid input, right? And the valid inputs are only natural numbers as we defined in our actual writing of the sequence. And as you can see, this sequence trends towards one value. If you plug in a very large value, so if you say that the limit as n approaches infinity, or the largest value that this countably infinite number of inputs can achieve, the limit as n approaches infinity of 1 over n, we think about this and we just say we plug in 1 over infinity, and we think in our heads 1 divided by a very, very big number is a very, very small number. And we say that this sequence will converge to 0, right? So, well, I haven't gotten to convergence yet, but we say that this limit, the limit of this function is, not function, limit of this sequence as n approaches infinity is 0. I got a little bit ahead and jumped the gun, but we're going to talk about convergence and divergence now. I know I didn't really go over limits of sequences particularly well, but I would say that for the most part, if you understood limits in functions, which I think I went over pretty thoroughly, it doesn't really hurt to at least talk about limits. I'll talk about the formal definition of a limit, or, well, I guess I'm going to be talking about the formal definition of convergence, but yeah, just in terms of limits, it's pretty much the same as in functions. If the n value is approached from both the left and from the right, then some output has to be approached from higher values and lower values, and you should get a limit, or the value that your function or sequence is tending towards. That's the idea of a limit, and I went over in much more detail in that limit video, but I think the same ideas apply. What is happening with the limit is generally happening with a sequence, and if you understood what was happening with limits and functions, then you can just apply the same thing to sequences. And like I subtly foreshadowed, convergence and divergence usually does work with limits, the same ideas behind them. So, I didn't really explain it, but convergence is the quality of having a limit. If a sequence converges, then it converges. Let's write down these ideas. Converges means that it has a limit. The n behavior tends to one value, and that is the limit. It's a limit as n approaches infinity of a sub n is equal to L. That's the limit. Or it is divergent. since I use convergence, I'll put like divergent or convergent, right? Because that's what we call these sequences. We say it's convergent or divergent, but the quality of having a limit is convergence, and the quality of not having a limit is divergence. So, not conversion. And that's a pretty broad definition of divergence, but you can specify a little bit further. For example, uh, well, so let's talk about how convergence really looks. We talked about it with 1 over n, but if you have, you know, values that the sequence is tending towards, right? Usually you can think of it like asymptotes, but if you get to a specific value as n approaches infinity, this is the limit, right? Even though it might not explicitly touch this limit, you are getting closer and closer to some specific value. And that means that you are converging to that value. But divergence is a lot broader of something to define, right? So, for example, if we go to a sub n is equal to n squared, and you are trying to find the limit as n approaches infinity of a sub n, we're going to have, well, n, which is, well, we're going to have n squared, and we're going to say that this is equal to infinity squared, right? Even though we can't square infinity, as infinity is not a number, we can obviously say that this will go to infinity. And since infinity is not a valid limit, we say that this sequence is divergent. But it doesn't necessarily have to go to infinity or negative infinity. There's something called oscillation, and I think that's best described by a sub n is equal to -1 to the n. Now let's write out some of the terms of the sequence. I'm not sure if I explicitly said it or not, but each output of a sequence for every valid input will give you a term. For a sub n is equal to n squared, if you start at n is equal to 1, if, the domain is n in natural numbers, if you start at 1, you're going to go 1, 2, 4, 9, 16, 25, and on and on. Those are the terms of that sequence, and you have, values for every input. So let's plug in n is equal to 1, right? This is going to be our first term. We're going to say -1 to the 1 is 1, right? And then, -1 to the 1 is -1. And if you plug in n is equal to 2, you're going to have -1 squared, which is +1. -1 to the third is -1. +1, -1, and on. So if you would actually graph this, let's say that this is 0, you're going to have values that look like this, right? And this does not have a valid limit. Because if you just sort of look at it, I think it's obvious that you're not really getting closer to any specific value. And as n approaches infinity, you could go to either, 1 or -1. So there are multiple limits or multiple potential limits, which means that there is no limit at all. And if you're wondering about whether or not it could be 0, I think that's a valid thought, but you have to remember that you're not actually getting any closer to 0. Since -1 to the n is only, valid for the n values that are integers, there can't be any decimal values, it can't get closer to 0 at all. And even if it was a function that was continuous for all real values of like x, it still wouldn't actually converge to anything. It would diverge. And yeah, that's oscillating. I can even write that out. That's just a different way of saying divergent, right? This sequence oscillates, which means it goes from value to value, and there are only two possible values, and it just oscillates between those two. And yeah, that's just, a good thing to know. Oscillates is just another way of saying divergent, right? -1 to the n diverges the same way, well, not the same way, but just as much as a sub n is equal to n squared, but only one oscillates. So now that we have a general idea of convergence, I think it's important to reeval- reevaluate our definition of convergence. This is going to be pretty similar to our formal definition of a limit, but we say that um, a sub n a sub n converges to a real value L. You might be wondering how this is possible, right? Because how can you get a, well, decimal or something if you only have natural number inputs? I think if you just thought about it like square root of n, um, a sub n is equal to the square root of n. This is a completely valid uh, sequence, right? Even though you might not have uh, like natural number outputs, you're going to have natural number inputs. And that's the most important thing about these kinds of sequences. The inputs have to be on a defined range or defined domain of natural numbers or integers, but the output can be real values. Right, so we say that a sub n converges to a real value L, real value L, if for all epsilon greater than 0, there exists, okay, starting to forget if this is how you write there exists, right? Yeah, I'm confusing myself. This is there exists, right? If for all epsilon is greater than 0, there exists a natural number n, so a n in n, such that for all n that is greater than or equal to n, we have a sub n minus the limit is less than epsilon. So again, you just sort of think of this as a tolerance, right? If epsilon is a value that is greater than 0, so you can think of it as just a very small sort of value, like a very low tolerance, then there has to be an L. Like if you say that a sub n, like the value that you are getting closer and closer to, minus L is less than epsilon, which is already inherently a small value, as we sort of, said. We say that this is the limit. L is the limit, and that well, I think you might even see this in some of your future math things. You have the distance between a and a sub n and L. This is like a function on some calculators, I think. I don't know. But I've seen this before. It's just saying that this is the distance between the actual value that this converges to, or the absolute maximum, like, inputs output, minus L is the distance between those two, and that's going to be less than epsilon. And again, the reason that we have the absolute value is just to account for both negative and positive values, because tolerance should be able to include both. Let's write this out. We're going to have both negative epsilon and positive epsilon, right? If we have negative epsilon and positive epsilon, and epsilon is a small value, right? That means that, well, a sub n and L are getting very close to one another. I think that just sort of makes sense. Like if a sub n and L, which is its limit, are very close, which they should be, a sub n is supposed to converge to L. That means that for a very small epsilon, you are going to have these two values be very close to one another, or for our purposes, essentially be equal to one another. And the ideas behind limits for functions follows the same ideas of limits in sequences. Right? You can do the same type of operations with limits as you can with functions. So let's write some of those operations out. You can do the limit as n approaches infinity of, and I'm just going to say a sub n and b sub n, right? Because it doesn't necessarily have to be a, but this is equal to the limit as n approaches infinity of a sub n plus the limit as n approaches infinity of b sub n. And I'm actually going to do something that I don't typically do. I'm going to not do the proof of this, or for any of these. I know, that's very out of character for me, but I've already done the proofs for the actual limits, like these operations in, my limit video. And again, as I've been saying, like, if the sequence converges to a limit, then you are doing the same type of things that you're doing with functions, right? You're doing the same limit evaluations and behavior, and you are going to get converging values, and you're still doing what you're doing, but, you're just using different terminology. Like, again, sequences and functions are very similar, it's just that sequences have different possible values, like different possible inputs. They're only, valid for specific defined, like, intervals, usually n or z, and functions are almost always defined exclusively on r, every real value, on negative infinity to infinity. So let's go through some of these. You have the limit as n approaches infinity of a sub n plus or minus b sub n is equal to the limit as n approaches infinity of a sub n plus or minus the limit of n approaches infinity of b sub n, which means that you can separate limits as you could do with normal functions. The limit as n approaches infinity of c times a sub n is equal to c times the limit as n approaches infinity of a sub n, which means that you can factor out constants, right? And then the limit as n approaches infinity of a sub n times the limit as n approaches infinity of b sub n is equal to the limit as n approaches infinity of a sub n times, or, well, kind of messed that up. I'm just gonna write it out here. I'll technically, the way I should have written this was just like flip these two so that I'm consistent with my previous two statements, but it's the same thing as a sub n times b sub n. And you can write that down if you'd like, but as long as you know some of the rules behind normal limits, I think you'd be fine with applying those same rules to sequences. And we're gonna do, I think, two more good ones. We have the limit as n approaches infinity of a sub n over b sub n is equal to the limit as n approaches infinity of a sub n divided by the limit as n approaches infinity of b sub n, as long as this limit does not equal 0. Right, and then you have the limit as n approaches infinity of a sub n to some value. We'll say x is equal to, well, the limit as n approaches infinity of a sub n to the x power, as long as x is greater than 0. Because, if it was less than 0, well, if it was equal to 0, I think it's obvious that you won't get the same value. But if x was less than 0, you'd get fractions, and then you'd get completely different limits regardless. But, yeah, and a sub n should be greater than 0. I mean, it usually is, but, if you have negative values to odd values, you're going to have negative values. And if you have negative values to positive powers, you're going to have positive values. So it'll look like it oscillates when it actually does not. And yeah, I think that's pretty much it. If, well, we can also do squeeze theorem, but just to sort of say it out loud, it's if a sequence is less than another sequence, like say a sub n is less than b sub n, then the limit as n approaches infinity. And when I mean a sub n is less than b sub n, that means that every input of this is going to be less than every input of that. Then the limit as n approaches infinity of a sub n is going to be less than the limit as n approaches infinity of b sub n if the limit exists. Because, I mean, if a sub n and b sub n both diverge, then infinity is not less than infinity. Infinity is not equal to infinity. Infinities are all of different sizes and are inherently confusing. But that is not really like a theorem or anything. It's just something to remember. It's relatively obvious. But if C sub n, this is going to be another way of writing the squeeze theorem. If C sub n is in between two functions or sequences, we're saying a sub n and b sub n. So we're going to have a sub n, b sub n, and, n is like the possible natural numbers. Then we say that if the limit as n approaches infinity of a sub n is equal to the limit of n approaches infinity of b sub n, and it's equal to L, right? Then C sub n is going to be convergent. And it converges to L as well. This might be a little bit strange, like as an idea, but I want you to sort of think of it like this. So I'm not going to erase any of this, but let's say that you have this is a sub n, right? And, well, that's actually a bad way of drawing a sub n. Let's just put some dots, even though it's definitely going to get more confusing. So this is a sub n, right? And then this is, okay, I'm sorry. I'm sorry, I'm going to use function like drawing, but the same idea behind functions are applying to this squeeze theorem. So if a sub n is, well, we said that a sub n is actually the smallest function. If we say that this is a sub n, right, and this is b sub n, and this is c sub n, and a sub n is converging to this value L, and b sub n is also converging to this L, then c has to converge to this L. If c is bounded by two sequences with the same limit, then c has to have that same limit. And I think it makes sense that c converges, because if b converges and c is less than b for every possible output of c, then it has to converge to a specific value. And if the sequences that bound c have the same limit, then c also has the same limit. I think just like visually looking at it, it makes sense, because both a and b have the same like value that they're approaching, right? I know I didn't draw it in correct sequence way, because, I mean, it's just going to look like a bunch of random dots, but I hope the ideas behind it make sense. And now we're going to go through a nice, like, speed run. Or, well, let's talk about another quality of sequences. Let's see. Let's talk about, let's talk about increasing and decreasing, just in terms of sequences. So, within the idea of sequences, a sequence is monotonically increasing. Let's write that out. Monotonically increasing. increasing if and well, increasing if and only if um, every term is, let's say, every term is greater than the previous. So, for example, a very famous sequence, the Fibonacci sequence, where you add, well, let's talk about recursive sequences after this. But, just in terms of if you wrote the natural numbers as a sequence, right? 1, 2, 3, 4. This is monotonically increasing because every subsequent term is greater than the previous term that came before it. And if it is like, well, this is slightly inaccurate. Let's say if every term is greater than or equal to the previous, that means that it is monotonically increasing. But if it is always greater, like for the natural numbers, if it's always greater, that becomes strictly monotonically increasing. And as you may or may not guess, there is also monotonically decreasing, right? If every term is less than or equal to the previous term, then it is monotonically decreasing. But if it is less than every other term, you have a strictly monotonically decreasing sequence. And as I sort of mentioned beforehand, recursive sequences are sequences, well, you're not going to use this too much in, calculus, and I mean, I don't know, you might have to, but recursion is just, this is more of like a computer science idea, but you will probably use recursive sequences at some point in your life. Recursive sequences are just sequences that use previous output as input. And just for a 2-for-1 demonstration of strictly and like regular monotonically increasing versus like the differences between those and recursion at the same time, sequences that use previous outputs as inputs. Let's talk about the arguably the most famous sequence, and that is the Fibonacci sequence, right? Where you just add every previous term. Like, so you start at 0, or you can start at 1 if you want, but usually start at 0, and then you add 1, right? You get 1, you add these two, you get 2, you add these two, you get 3, you add these two, you get 5, you add these two, you get 8, you add these two. That was one of the worst 5s I think I've ever written. You have 3, 5, 8, then you get to 13, 21, 34, and on and on. Now, this is pretty famous. Like, there's a lot of things that are cool about the Fibonacci sequence that I don't think we have time to get through now, but just this is a recursive sequence, right? Every subsequent output, like 1, for at least the second one, was created from previous inputs, right? I mean, previous outputs. 0 and 1 are outputs, and you had to add them to get 1. And 2, you had to add 1 and 1 to get 2. Like 3, you added 1 and 2. You had to add previous outputs in order to get the now, in order to get your next output. So every, like, recursive sequence uses previous outputs as new inputs. And this, well, this is a monotonically increasing sequence. This is not strictly monotonically increasing because 1 and 1 are equal to one another. So every term is not greater than the previous term, but every term is greater than or equal to every other term. So this is a monotonically increasing sequence. But as I was saying, the natural numbers, like n, if you defined a sub n is equal to n, right, you have 1, 2, 3, 4. This is strictly monotonically increasing for every single possible n value, right? There is an output, and every output is greater than, strictly greater than, every previous input. Every previous output. So that's why, natural numbers are strictly monotonically increasing, but the Fibonacci sequence is not. It is only monotonically increasing. And now we have to speed run. I'm not sure. So I don't have too much time right now, but I do plan on talking a little bit more about sequences. I think maybe in like a very short addition video, like not addition that's in 1+1, but like some important ideas behind these things, right? Okay, wait. Let's also talk about bounds. This is, again, a very simple idea. If a sub n, if every output of a sub n is less than some big number, n, well, maybe I shouldn't use it n, because let's say everything is less than m, right? If every possible output of a sub n is less than a real value m, that means that a sub n is bounded from above, right? If you think of bounds, like upper and lower bounds, in terms of integrals, then this also works. This is considered like the upper bound of the sequence as a whole. This is the maximum possible output of a sub n is still less than the real value m, which means that the sequence is bounded from above. And for every n, I don't know if it's, I think it's upside down a, right? For all n in n, a sub n is less than or equal to m. That means that it is bounded from above. And of course, if it is greater than m, we say that it is bounded from below. Bounded from below. And a sub n is going to be greater than or equal to m for all n in n. And if there are upper and lower bounds, so if it is bounded from both above and from below, then this sequence is just bounded. Like, we just say it is bounded. And that's relatively intuitive. Like, if you say that, hey, this sequence will always be greater than 1, like, let's talk about the natural numbers again. If you say that this is 1, 2, 3, 4, 5, this is obviously bounded from below because every value is going to be greater than or equal to 1. And this is not bounded from above because, this will go on and on. It'll be 6, 7, 8, and, you can count on to infinity. But if we stop the sequence right here, if we said it was just 1, 2, 3, 4, 5, then it will be bounded from above, just to 5. And the sequence, since it has a beginning and end, will be bounded. And yeah, so I think that was a pretty good thing on sequences. I also do plan on talking about, just in an addendum, sort of like arithmetic geometric sequences, and that will take like 20 minutes, 30 minutes max. But it's like, I'm just going to talk about what they are, how they work, partial sums for them, and just some important-ish ideas about sequences. But again, this is a relatively short video because this is a relatively intuitive concept, at least if you've done, functions for most of your academic career, right? I would encourage you to watch my limits video because that's where I actually go into depth about what limits are, how they work, but you just apply what you know about functions to sequences, and you will do fine for the most part. But you do need to remember that there are some very distinct differences between sequences and between functions, right? Because sequences are continuous for a defined interval, usually n, but it can be z. Um, and there's a countably infinite number of inputs, and for, you know, um, normal functions, there is a uncountably infinite, an uncountably infinite number of inputs. So, yeah, I mean, relatively similar, but there are, very distinct differences that if you understand, like, the differences in possible inputs, that's probably the best thing to understand the differences for, and convergence, divergence, oscillation, like, I think if you get those, you are in very good shape to understand series. But yeah, I mean, there are obviously a lot more to talk about sequences, and I will talk about some of it. I'll be talking about just, just like the different types of sequences. Like I'm going to talk about oscillation further. I'm going to talk about arithmetic sequences, Cauchy sequences, a little bit probably about geometric sequences, recursive sequences, harmonic sequence, and just random, like assorted ideas about sequences that I feel are necessary to know. And we'll go through that relatively soon. I'd say it would take maybe 30 minutes. Just gonna talk very briefly about what they are, and then we can get to the real meat and potatoes, and that is series. Um, just as a, you know, precursor to what a series is. I'm just gonna say it out loud. Series are just the sums of every term in a sequence, at least for us. And we can do infinite series and Taylor series and Maclaurin series and convergence and divergence of series, and there's a lot to go over. But as long as you understand a good bit about sequences, as I think you do now, I think we'll be doing fine. And again, this is a rather short video, so I don't feel the need to recommend a full album, but I have been listening to quite a bit of samba jazz recently. Um, well, I'll save the samba jazz album for later, but I I know I'm very late to this party, right? Like I know it is long gone in terms of cultural relevance. I mean, that's where most of my songs come from, long gone from cultural relevance. But Calvin Harris, I heard this song a long time ago, but I remember I was really edgy when it came to music, and I refused to acknowledge that pop music was good. I don't even remember like, the artists who were featured on the song, which is not good because I've listened to it at least a dozen or so times in the past couple of days. But Funk Wave Bounces, like Volume 1, that full album is honestly pretty expansive. In terms of like the sounds that are on that album, it is very diverse and interesting, I would say. There are a few weaker cuts, but I'd say Feels is probably one of my favorite pop songs that I've heard in a long time, which surprised me because I remember I used to get really annoyed by any pop at all. So now the fact that I've gotten into like art pop and like, you know, pop in general, I'm never getting into hyper pop. I can put that on the record. But now that I've gotten into pop more broadly and I've become less of an elitist, I would say Feels is a pretty good song for what it is. And that whole album, Funk Wave Bounces Volume 1, I would say is worth listening to, even though there are a few songs that I will skip. But just in terms of a description, it's a very lush instrumental. It's very fun. Like I feel like it's a perfect song to like drive to if it's like 100 degrees out. It's a good summer song. So yeah, that's generally my thoughts on it. And if you, oh god, I forgot my outro. Um, if you like this video, um, But if you like this video, please comment down below. If you did not like this video, constructive criticism is always encouraged. And if you're not in the mood for a comment or constructive criticism, then you can do some rows. Some rows are nice. I've been doing a lot of rows, and they are very exhausting. But yes, good job, everybody. I really need to get back onto this whole recording thing. It's been far too long. Alright, bye.